first of all, we'll just say what is say what is this square law. Like Newton said that every object in the universe attracts every other object with a force which is proportional to the product of their masses and inversely proportional to the square of the distance between them. Okay. Yeah. So this was basically inverse square law. So there's actually, we can say there's a story behind how he found out this inverse square law. So before coming into that story, for the basic we need to know before learning this inverse square law, the Kepler's laws of planetary motion. Okay. So there was a scientist, not a scientist, basically he was an astronomer and a physicist and all. There was someone called Johannes Kepler, and he had derived 3 laws which was used to govern the planetary motion. Okay. So the Kepler's 3 laws said that, in that the first law, okay, so the first law of Kepler, that is the law of orbit, we can say. Okay. So the Kepler's law of orbit said that the planets move around the sun in elliptical orbit with sun as one of the precise. Okay. So that was the law of orbit. So the law of areas, that is Kepler's law of areas, said that the line joining a planet to the sun sweeps equal areas in equal interval of time. So that was the second law. And the third law, that is the law of period, said that the square of the time period of the planet is directly proportional to the cube of the semi-major axis of its orbit. Okay. So that there is an equation. There is a proportional equation in this third law, that is r cube by c square gives a constant, where r cube is that radius and c is the time period. So r cube divided by c square gives a constant. Okay. So Johannes Kepler equated these 3, gave these 3 laws. But what happened is, at that time, Kepler was not actually sure about how this planet moves. Because, see, these planets are moving in elliptical orbit. Let's say it is like around similar to a circular movement. Now we know how it is moving. But that time, Johannes Kepler didn't know how these planets came into this motion. Okay. So, the Newton Newton was actually thinking over it and how the planetary motion is happening, basically. Okay. So, as we have all known about that story, Newton found gravitation when the apple fell on him, on his head. Yeah. So he found out there is a force called gravitation. Okay. So there is a force of gravitation which is exerted. So connecting with these things, with the planetary motion and all these things, Newton actually came up with an idea that there is some force which is helping this planet to stay in that orbit and rotate around the sun. Okay. So that force is basically the centripetal force. Okay. So just not even considering the planet, if I am having a stone and if I am tying it to the end of a thread and if I am whirling, so that's the stone is continuing in that circular motion because there is a force which is helping that stone to move in that direction. Okay. So this force is centripetal force. Centripetal force, which is, we can also call it as a center-seeking force, is the force that acts on a body moving in a circular path that is directed inwards to the center of the circular path. Okay.
Okay.
Yeah. So the same thing is happening in case of planetary motion. So when it comes to the planetary motion, what acts as centripetal force? The gravitational force. The gravitational force between these heavenly bodies acts as a centripetal force and help in the movement. Okay. So, yeah. So, Newton showed that gravitational force is the cause of this planetary motion. Okay. So, after that, he was thinking of it and he wanted to equate this and he wanted to find a relation. So, he simply came up with an argument that the gravitation of two bodies will decrease, will get weakened when the distance between that bodies increases. So that was just an assumption. Then he started working over it. Okay. So what happened is, he compared this planetary motion with a falling apple. Okay. So we know there is a centripetal force. So as we have said, centripetal force F is directly proportional to V square by R. Okay. That v square is the velocity and r is the radius. So you can note it down. Yeah. So that centripetal force F is directly proportional to v square by r. Okay. And we know from the Kepler's law, that is the third law, r cube is directly proportional to t square. Okay. So we know these two things. So when we are considering these two things, when we are equating these two things, we will get a relation that is the velocity v is proportional to radius r divided by time period t. That is v is proportional to r by t. Okay. Yeah. So with that, he started equating and he came up, what he did is he considered as always like two bodies. Let us say any two bodies. In this case, he was considering about the planetary bodies. Okay. So he considered the planetary bodies. That is, suppose there was a two planetary bodies and the orbital velocity is v and radius of orbit is r. Then the force acting on this orbiting planet is given by Fv square by 2. If t is denoted by the time period, then we know v is equal to 2 pi r by t. Then as I have already told, v square is directly proportional to r square by t square. That is, v is proportional to r by t. Then he got the formula, that is F is directly proportional to 1 by r square. Okay. That is, F is directly proportional to 1 by r square. Okay. So there comes the relation. When the force is increasing, it is inversely proportional to the square of the distance. That is the distance. Okay. Orbital radius. So then he used this equation between two bodies which are separated by a distance. Okay. So then he took two bodies which is separated by a distance and having mass like m1 and m2 or capital N and small n. Then if it is separated by a distance d, then he mathematically found out that the force acting, that is directly proportional to the product of the mass and inversely proportional to the square of the distance between them. And to equate this proportionality, see, whenever we want to equate a proportional constant, like if you want to change that proportionality symbol to an equal to symbol, we need to add a constant, right? So there came with the constant, universal gravitational constant, that is capital G. And the value of this capital G was found as 6.67 into 10 raised to minus 11 Newton per meter square by another scientist. Yeah, that was the Henry Cavendish. He found out the value of this using, it was like a balance. It was an observation basically. Okay. So what does Henry Cavendish do? What he was experimentally determining this value. Okay. So he used the torsional balance. That is, it is an apparatus having 2 feet long, one rigid rod, and it will be having 2 spheres attached to the both ends. Okay, that is this balance. A long rod and 2 lead spheres attached at both ends. Then he will be suspending this with a thin wire. That was the experiment he did. Then he found out with many observations and many calculations, he found out the value of G, that is 6.67 into 10 raised to minus 11 Newton per meter square, Newton meter square per kilogram square. Okay. So this is basically Newton's inverse square law. Okay.
Okay.